record button and start. So welcome everyone to yet another Friday afternoon webinar. And now also a collaboration between Norwegian Open AI Lab in Trondheim and Nora. So it's my pleasure then to show you that we will not only collaborate today, and we have done this before also to other webinars, but we will have a series this spring. So the next speaker will be Robert Jensen, 28th of May. He's a professor at the University of Tromsø, the Arctic University. Then we will have a startup webinar. This will be probably about audio and startup companies joining forces with the researchers. The June 11th, Christian Balog will have a research talk from professor at the University of Stavanger. And then again, 18th of June, another startup webinar. Then it will be collaboration between students and startup companies. I think then also NTNU Brain will also be there at the 18th of June and several startup companies. This is the program for the spring. So you're all welcome to attend those future meetings. Trym Holter from NAIL will present today's speaker.
Thank you, Klaus. It's a pleasure, of course, to introduce Øyvind Smogeli. Øyvind received his PhD from NTNU in 2006, and he has spent his career working on modeling, simulation, testing, and verification of complex cyber-physical systems and assurance of digital technologies. He has held positions as CTO, COO, and CEO of Maritime Cybernetics in Trondheim, and also as a research program director for digital assurance in DNV. And on a personal note, also in DNV, Øyvind, you were our contact person for the Norwegian Open AI Lab. So thanks for that collaboration. Øyvind is currently the CTO and co-founder of Zeabuz, and also from recently an adjunct professor at NTNU. And the title today, I think, reflects something that's very important for you. It's building trust in autonomous mobility systems. So over to you, Øyvind.
All right. Thank you, Trym. So then let me share my screen. All right. So thank you for inviting me for this webinar. It's a pleasure to be here and to present a bit of what we're working on at Zeabuz. I will talk about these challenges of assuring autonomous mobility in general, but of course I will use our application, which is these small autonomous electric urban passenger ferries that you see in the picture here. So this is a vision of what it will look like. Well, hopefully you'll see the first one on water already next summer. So it's not that far into the future. I think Trym, you gave a good introduction of myself, so I won't spend time saying more about me. I would rather just jump into the presentation. What I have in store for you today is a short introduction to Zeabuz and what we are working on. Then moving on to the challenges of assuring these systems. We'll have a look at what's going on in automotive and in the maritime industry. And then I will show you what I've called a preliminary assurance toolbox. Preliminary because this is very much work in progress and it's research in progress. So there's no set answers to this, which also makes it fun to work with. And then say a bit about how we plan to kind of scope and structure the assurance process in Zeabuz with our system. And well, if time allows at the end here, say a bit about how we use simulation as part of that assurance process. So yeah, let's move on. This is what we're trying to solve in Seedbus. Roads have become overfilled with traffic and cities keep growing. But the old waterways that are basically the reasons why cities were put there in the first place, because they used to be main mode of transportation. They are pretty much unused. We believe it's time to change that and take our historic infrastructure, the waterways, back into use. And our way of doing it is through concepts like this, through zero-emission, autonomous, waterborne micromobility. So for those of you here in Norway, this picture might look familiar. It's from Oslo, from Bjørvika. This is the barcode you see in the background. Actually, today there is a floating bridge here between what's known as Sukkerbiten and Sørenga, and it's quite well, it's a lot used, especially in summertime. But that floating bridge is going to be removed, and we believe, of course, it's a great idea to put a Zeabuz transport system there instead. So this is kind of a perfect example of where we want to start. It's the simple, small shortcuts across canals and rivers and harbor basins, so which basically gives you a very simple, what we call operational design domain. So there's not a lot of traffic. The weather is and the environmental conditions are usually pretty calm, it's short distances, it's close to shore. So it's a rather simple problem to solve, but still challenging. And of course, this concept is very much in line with sustainable development goals and the European Union taxonomy on sustainable development and so on. So that's all good. We can tick all the boxes. So our vision in Zeabuz is to empower communities to allow citizens to travel across these urban waterways around the clock, around the week. One of the challenges today with waterborne mobility is that because of the cost of crew, the time schedules are very limited. If we remove the crew and we go autonomous, well, they can be available 24/7 and on demand. We also then offer urban developers a new mobility mode to provide flexible shortcuts between communities. For example, connecting a new residential area to the city center. So we're talking actually with many Norwegian cities these days that have these kinds of challenges. They have new areas they want to take into use, but it's hard to connect them to the city center through land-based infrastructure. So and globally, there are loads of opportunities like this. And of course, finally, we want to enable cities to become cleaner and more attractive by improving mobility flow. So as cities are growing and roads are becoming congested, this could alleviate a lot of the passenger traffic. So people on foot, on bike, on electric scooters and so on could use the Seedbus solution in connection with other micromobility solutions to move about the city in an efficient way. So that's what we aspire to do. So that was short, about Zeabuz and our vision for the future. I should, of course, mention that Zeabuz is a spin-off from NTNU. So there's been decades of research on autonomy, and in the later years on this kind of waterborne micromobility in particular. So NTNU has the world's first pilot ferries, the Milliampere, which has been on water for some years, and are just now putting the finishing touches to the Milliampere 2, which will be put into trial operation in Trondheim this summer. And we are, of course, helping out in that process. So this summer, it will be possible to, as a guest, to take the world's first autonomous passenger ferry in Trondheim. And based on that experience, we are building the first kind of commercial solutions. All right, so let's move on. What makes this challenging, and what are the main challenges in building trust in these systems? Because of course, trust is essential. If people don't trust that an autonomous ferry is safe, they will not use it. So in my work as a CTO, I feel like I have kind of two main paths. And we're working on the autonomy technology itself, so the operational technology that will make these ferries and the whole mobility system work. And in parallel, we are working on the testing and verification technology. So it's a lot of simulator technology And also, we're going to, of course, need to do a lot of full-scale trials and testing and so on. But the effort we're going to spend on building trust in the system is just as big as the effort in actually making the systems. And the reason for this, hopefully, I'll be able to explain to you now when you see the challenges that we are facing. So I've tried to structure this. You could probably slice and dice it in many different directions, but at least this is my attempt at structuring my own thoughts on the challenges. So, I mean, we are already dealing with complex software-driven systems. And this is what I've been working on for most of my career, is testing and verification of these kinds of systems in the maritime space. So control systems on ships and offshore installations. And this is already a big challenge, how to make sure that they always work as they should and that they are safe. So it's challenging even before you introduce autonomy and AI. So when you add AI on top of this, because of course to make it very autonomous, there is several parts of the system which needs AI. So it's machine learning in the machine vision. There's some pretty sophisticated algorithms in the situational awareness and the motion planning. So we have additional layers of complexity that we add on top of already pretty complex systems for the ferry. This, of course, means that it's not really possible to prove that it's safe. For simpler systems, there are methods and tools that you can use to prove stability, and you can have these formal methods to prove that something's safe. But for these complex systems, that's not possible. So you need to resort to statistical demonstration of safety. And this is exactly the same problem they face with autonomous cars. So the big question becomes, what's safe enough? So how much testing and verification do you do? How much do you prove before you consider the system to be safe enough? Then we have the challenge of lifecycle change management. So these systems with this level of complexity and all this software, they're going to change a lot. I mean, you can see it already if you look again to Automotive, look at Tesla. They are updating the software of their cars, pretty much, adding functionality, adding feature, making them better. It's the same physical car, but it's changing through the life cycle. And our systems will do that too. And we need to manage that. So having put down a huge effort to build trust in the system, and then the week after you update it, how to kind of handle that process to make sure that you don't break the system and breach the trust. Then, of course, with these kinds of complexity, I mean, both the system complexity and the complexity of the operations, there will be some unknown scenarios. There will be some unknown unknowns, some black swans, to use that term, that we don't know. We cannot really account for it, but somehow we need to try to build systems that are robust and resilient towards those kinds of situations, although we cannot prove it anyway. And finally, there are some big challenges in human-machine interplay. So although these systems will be autonomous, there will always be a human in the loop somewhere. I mean, there will be human developers, at least for the foreseeable future, that are developing these systems. And then in operation, there will be an interaction between the passengers in the ferry. There will be an operator at the remote support center that's providing remote assistance and can communicate with the passengers and take control of the ferry if necessary. And there will be an interplay between the ferry and other manned vessels. So all of this raises unknown questions: how they will interact. What if someone tries to bully our autonomous ferry by just a swarm of kayak paddlers just trying to push it to see what happens, or someone just lying in front of it? So there are many scenarios that's hard to think of all of them. So and of course you also have this, as I said, the interaction with the passengers where unknown situations could occur. So all of this is challenging when we try to build trust in these complex systems. So, but of course, if we want to succeed, we need to be able to build that trust. So to dive a bit deeper into some of these dimensions, I'll do a couple of dimensions of this to maybe trigger your curiosity a bit. We have the challenge of technical versus perceived safety. And actually, I stole this kind of graph for this layout from Aptiv, which is one of the major players in automotive autonomy. But this is, when you think of it, this is really a big challenge. In this, you have two axes. You have the perceived safety, so the kind of the public acceptance of the safety of the system on the horizontal axis, and you have the technical safety, the actual safety, on the vertical axis. So on the vertical axis, then, if you have high technical safety, well, the system is safe, and it can be documented to be safe. And this is this is a technical problem, which goes back to a lot of the challenges that I introduced in the last slide. But on the other axis, it's not about proving that it's safe. It's about making sure it feels safe, right? It should inspire confidence amongst those that use it. And this might actually be just as hard or even harder to solve than the technical problem of proving safety. So of course, where we want to be with Zeabuz is in the top right, so that it is safe and that it feels safe. And if you are on the wrong place here, if these two elements are not in balance, you'll get in trouble, right? If the system is not safe but feels safe, then you're kind of bound to have accidents. Again, I'll probably use Tesla a couple of times as an example because I think it's a fun company. But if you look at what's happening with their autopilot, humans, we are easily kind of lured into believing something's safe if you just observed it's worked for like 5 minutes. So people, letting go of the steering wheel and climbing into the back seat to have a nap and then die in a crash, that's because they have a much higher perception of the safety than the technical safety is really capable, than the system is able to do, right? So the perceived safety is higher than the technical one. And of course, if the system is safe but doesn't feel safe, well, people just won't use it. So that's one challenge. Another challenge we have is to balance safety with performance. So here again, we have two axes. I like these diagrams with two axes. We have the performance of the system, or the usefulness of the system, on the horizontal axis, and we have the safety on the left, on the vertical axis. So try and come up with a system or an example which is not very useful and not very safe. This could be an example, a flame-throwing drone. There might be some useful applications, but I haven't thought of it yet. So let's try to have a fun example. But in this quadrant, something that's not very useful but very safe, it's a parked autonomous car. This has been kind of riddling the autonomous car industry from the early days, is that in order to stay safe, they would stop whenever they thought they saw something. And because the machine learning system, machine vision, and the LiDAR systems were not that good, they thought they saw things all the time. So the cars barely moved, right? So it's pretty safe, but it's not very useful. Then on the other axis, if you have something that's high performance but not very safe, you get into other kinds of trouble. So here I'm using the example of Uber. It's now a pretty famous accident where they killed a female pedestrian walking a bicycle in Arizona. And the background here is that they had tweaked and tuned their autonomy system to give a smooth ride, a nice performance. It should feel, it should feel good. But the way they did it was by saying, if we don't understand exactly what we see, we just keep going. And then the machine learning algorithm didn't recognize a female walking a bicycle outside outside kind of the normal place they would expect to see someone. So they didn't understand what it was. She was detected quite early, but kind of categorized wrongly and then recategorized. And all the time while the system was pondering what this was, they just kept going. And when they figured out what it was too late. So if you try to go too high on performance without while compromising safety, well, accidents are bound to happen. So again, of course, Seedbus, we will stay on the high quadrant. It should be useful and safe. And if you miss that balance, again, either it's you're out of business, or you get accidents, and well, you're out of business anyways. So to sum up these two slides, it's kind of this this triality of the perceived safety and the technical safety and the performance. We need to find a way to balance all of this when we build trust. And then there are, if I remember in this hexagon I showed, there's many many dimensions, but since we are at the AI Lab and the NORA webinar, I thought I'd just pick up one particular item out, which is the challenge of trustworthy AI, which is something that's close to my heart, and also one of the reasons why DNV joined the Norwegian Open AI Lab, and I was in the middle of that dialogue back when I was in DNV. So AI is of course challenging to build trust in, because it's so opaque in many cases. And I think I have a citation here in this slide on the top. I don't know if you can read it, but this is from an association called the AI Safety Work Group. And basically what they say, and which I very much agree to, is that the technical foundations and assumptions on which traditional safety engineering is built is inadequate for systems with AI. And this, of course, becomes a big problem when you have autonomous vehicles. So they have introduced some themes or topics to structure those discussions on how to discuss AI safety. So that's a useful resource without diving deeper into that. There is a nice document from the European Commission from the high-level expert group on AI, giving ethics guidelines for trustworthy AI. Although this document is not really focusing that much on the kind of cyber-physical systems that we're dealing with here. It's a lot about how AI and machine learning is used in other contexts. So to kind of try to bridge that while I was still in DNV, so it was DNV, now it was DNV GL when I was there, and now it's DNV again. So, but at that time we wrote a position paper that we called Trustworthy Industrial AI Systems. And here we try to focus on the applications that were close to DNV, which is really about machines that interact with the real world but get embedded AI into them. So autonomous vehicles is a prime example. So those are some references on this. It's I guess this could be a whole talk in itself about trustworthy AI, so I won't spend more time on it here. But this is a big challenge, and also something that's a big topic in the Norway SFI, which DNV is also part of. So I'm happy that there's a lot of active research in this field that hopefully we can use in Zeabuz. All right, so let's have a look then. I've already talked a bit about automotive, but just a quick glance at what's happening there, and to kind of to back up some of my statements later. There's yeah, a lot of talk about Waymo. I would say many claim they are the leader in autonomous driving. Formerly the Google self-driving unit. Now Waymo was an independent Alphabet company, and you can see this article here. It's not brand new, but it says Waymo has driven 20 million miles on public roads. 20 million miles with autonomous driving. That's quite a lot. But what I find more interesting is this article here, saying Waymo has driven 10 billion autonomous miles in simulation. So what they have seen is that even though they have this fleet of cars, they're getting all of this operational experience in the real world, it's nowhere close to enough to build sufficient trust in their systems. So they need to resort to simulation. So they are simulating driving scenarios at huge scale. And what we've seen is that this repeats itself. So every serious player now in the automotive domain are doing large-scale virtual driving in using sophisticated simulators that they can deploy their autonomous driving systems in. And there's also other things going on. This document that popped up in the wrong sequence here, Safety First for Automated Driving. It's a publication that was made by a consortium in automotive, laying out a lot of principles for how to build safe automated driving systems. Nice reference. It's been a bit inspiring to me, at least, trying to translate some of this over to Maritime. Other documents on what's safe enough, going back to my comment about statistical safety. Companies like this one is from Intel, trying to build algorithms that kind of replicate human behavior into into a machine setting. And yeah, another safety report. So these are just examples. There's loads of things going on in the automotive space. Huge investments being put down over the last decade It's completely crazy if you look at the scale of things. So, but what I try to do, based on what I've been reading up on and finding in the automotive, I try to kind of find the best practice development and testing strategy that we can adopt in Zeabuz. So what we see that they're doing is that they are doing what I call modular simulation. So there's a lot of building blocks in these systems. So they are simulating and testing them individually first. Then they do simulations end to end, so the whole system integrated, like a full virtual test drive. Then they do structured testing on closed tracks. Then they take them on public roads. And then you need to have a good system implemented for regression testing so that you can repeat this. And this loop just kind of goes over and over. But the point is that you cannot just test this in real life. You really need all of these simulation tools to be able to do it. And we also see that there's a growing ecosystem of simulation and assurance providers. So some names here probably look familiar, like NVIDIA. But there are companies now with huge valuations that are actually working exclusively with building trust in autonomous driving systems through simulation. All right. So some key takeaways, if I kind of try to look at these challenges and what I've learned from automotive, is that what I've learned is that functional safety is not enough. So functional safety is really what has made our current cars as safe as they are. So there are very rigorous standards that all systems in the cars are developed by. So the fact that our current, ABS brakes and things like anti-spin systems, things like engine control, that all of this is so safe is because of this standard. But when it comes to autonomous driving, you need new standards, and they are in the making, but they are very immature. What we see is that in order to succeed, they need huge amounts of real training data and field verification, but they also are leaning heavily on simulation. And we've also seen that there is this approach to building trust, which is called a safety case, which is spreading. And luckily, that's also the approach that we've chosen. Actually, before I learned that, in Seedbus, where we have a big research project together with DNV and NTNU on how to build trust in these systems, and we've chosen what we call an assurance case approach, which is really just a generalization of a safety case. So a lot of good takeaways here that I'm taking with me into Maritime. So then the question is, what's going on in Maritime? Well, that's again, probably it could be a talk of a whole seminar. But IMO, the International Maritime Organization, they are working on this. But the problem is that with all the member countries in the UN, they are not really an efficient organ to set out new routes. So all global traffic or all global shipping is according to the IMO standards or conventions is what they called. And they are not today fit for autonomous operation at all. They all refer a lot to the human role on the ship. So internationally, it's still a long way to go. The good thing is that nationally, the national authorities can give permissions. So in Norway, the Norwegian Maritime authorities, they are able to provide exemptions in national waters. So for us in Zeabuz to set up an operation in Norwegian city, we luckily don't need to worry about IMO. We can only deal with the maritime authorities in Norway. So, and the maritime authorities and DNV are quite forward-leaning and are working pragmatically to find ways to make this come true. So we still need to apply with Norwegian laws, and there's loads of laws regarding the operation of ships. So we need to find ways to kind of bridge those gaps that you introduce when you take away manning. But the good news is in Norway, at least, this is fully possible, and also working with other national authorities, you can make it come true, in country by country. Although the global shipping will still be a challenge for quite some time. So that was kind of automotive and maritime at a very short glance, just trying to give you a taste of what's going on. Then I thought I would dive into what I call this preliminary assurance toolbox. And before I kind of show the toolbox, again, just to illustrate the complexity of this, I thought I'd try to summarize some of the dimensions and stakeholders that we need to deal with when we build trust. So when it comes to the different dimensions there, I already mentioned, the technical safety and the perceived safety, which are connected but still different. We need to deal with cybersecurity. I haven't talked about that until now, but that's a huge issue as well. Of course, if someone is able to, take the passengers hostage and drive around with this autonomous vehicle, that would be, well, easily put someone out of business. The rules and regulations I mentioned, that I mean, we need to account for whatever prevailing rules and regulations that are there. So that's something you simply need to deal with. But then there are also some non-technical dimensions here that are important for business. We need to deal with ethics and societal impacts. So how the general public and the passengers welcome this new mobility mode, and also the environmental impacts. So how does this fit into a new a future which is greener and better? So those are some dimensions we need to kind of worry about when we or take care of when we build trust. And then we need to deal with all these different stakeholders that all have a role to play. The regulators are of course extremely important because they kind of set the baseline. Insurance companies are going to be important. The municipalities or in cities where these systems are being deployed, the passengers that will use it, other marine traffic, and also the kind of ecosystem around the mobility system, so the owners and suppliers and so on that will actually have a commercial stake in this. So somehow when we work on this, we need to account for all these different dimensions and stakeholders. So I think to us, it's important that we have this kind of holistic view. Looking at a lot of the work that's being done in automotive, they're very focused on safety only, which is why they work on this, what they call a safety case. And then all these other dimensions is not really talked that much about. And actually, if you dive deeper into it, I mean, making cars autonomous in itself is actually a pretty bad idea. If that means that everyone is going to own their own autonomous car, it'll only lead to increased congestion because suddenly those that don't own a car today will be able to own a car, and everyone will want their own car to drive around them. So actually, autonomous cars from a societal and environmental perspective only makes sense once you go into the ride-sharing approach, as well, at least in cities. So, but we want to look at the full picture here for our system. So that takes me into this assurance case approach. And as I said, the assurance case is then the kind of generalization of a safety case. It consists of claims, a rationale for what kind of evidence you would need to substantiate that claim, and the actual evidence supporting the claim. And this can be structured in many ways, but our main idea is that this should be transparent to all stakeholders, so that we can have these claims, we can collect evidence from a lot of different sources, and we can make it transparently available to all the stakeholders that would like to assess what we're doing. Yeah, so as mentioned, so this, you can kind of have a subset of the assurance case as a safety case, only focusing on the safety. And then you can say maybe the business case is a part of this. And I just recently listened to SINTEF Digital presenting what they call the trust case, which is also kind of a subset here. So we're trying to put this into the assurance case. All right, so what are then these different parts of the toolbox? Well, I briefly mentioned formal methods and kind of stability proofs. So, of course, for small parts of the system at the moment, we might be able to prove that it's stable and safe, which is useful because that means you can kind of take that out of the equation when you do the rest of the assurance process. But for the time being, these formal methods are only applicable to relatively isolated and simple systems. So it's also an ongoing research topic here at NTNU, especially up at Marine Technology, to look into how formal methods could be used for bigger and more complex systems. So if we can succeed in that, it's certainly going to help a lot, because without that, we kind of are stuck with this statistical demonstration. We have the topic of rules and regulations and standards, which are important to build trust. So if you have parts of the system that can be certified according to existing standards, as they do in automotive, that's a good idea. That's part of the trust building. And of course, in that also using third parties, like us in Zeabuz working with DNV as a third party to build trust in the systems. Then, in order to build trust, you need to have good and transparent processes. So this is kind of part of that you need both process assurance and product assurance. So the process assurance is really about ensuring that the way you work, the way you develop and deploy your products are of good quality. So for example, ISO 9001, that's a a process standard. So we need to deploy good system engineering principles, work diligently with hazard identification and risk analysis, and have traceable processes in the development and delivery of these systems. So you can say it's not this is not kind of disconnected. It's very much interconnected with the development process itself. Then use the arrows the right way. That's a good idea. Then we have what we call verification and validation in formal methods. So this is where simulator technology comes into play, and this is where I've been spending most of my career. Although I realize working on this that there are a lot of dimensions that we cannot handle by simulation, it's still going to be a very important part. So but informal methods then include full-scale testing, deploying the system out in the open in the real world, either in full operation or in kind of controlled trials. We have simulator-based testing of different kinds. We have runtime monitoring, which is important, also connected to the next point, the digital twins, which are digital replicas of the real systems that we can use to monitor and diagnose and work with the live systems through its digital counterpart. And regression testing, which is something that we need in order to make these processes more efficient. That, as I mentioned, if we have this big assurance case and then you update your system, you cannot do it all over again. You need to make sure that you're able to kind of isolate the change and make sure it doesn't have any kind of ripple effects that you don't know of. Then I have a kind of a big bag of things which I haven't been able to fit into anything else. I've just called it non-technical impact analysis. But in the part of building trust, you need to worry about a lot of different dimensions. So we have this what I've called the non-technical impact analysis. So legal and liability taken into account. We are actually actively working now with citizen engagement to understand citizens and their concerns and needs from such a system, and also with other stakeholders. As I showed you in the previous slide, this whole range of stakeholders we need to work with. We need to worry about impacts on the environment, so sustainable development goals, including the environment is important. The human-machine interaction analysis, bit about that in the beginning with the challenges. How will this machine interact with humans in different dimensions, both the passengers, the safety operator, other traffic, and so on. And also, we need to really understand the operational design domain. I've called it traffic analysis here. Maybe you could call it ODD, the operational design domain. But really understanding the local specialities of each location where you deploy the system, to understand what kind of features and abilities the system needs to have. And finally, since this is a talk with in the AI lab and Nora, I've extracted assurance of AI as a separate topic, and I didn't do that because of this talk. It's been like this all along, simply because AI is a bit different than the rest of the systems. So we need to take care to handle it properly. So I mentioned these trustworthiness principles. I believe that's a good start. We need to try to modularize and contain these systems so that we can make sure that they don't go beyond bounds. And of course, work on explainable machine learning is really interesting for us because explanations are an important part of trust. But what we see is, for the moment, there is a strong link here between building trust in AI and these informal methods, using simulators to build trust in the AI parts of the system. So this is it's a big picture, it's a lot of different dimensions, and as I said, this is very much ongoing development and research. So if you have comments, feedback, ideas, whatever, to this picture, I'm very happy to take it and happy to have discussions, because I mean, this can probably be sliced and diced in many different ways, and there's probably things I have left out or things that are inconsistent, but at least I'm trying to paint the picture here of the complexity and all the tools that we need in our toolbox to build trust. But as I said, very happy to take comments or feedback on this, either after my presentation or after that. Good. So then let's move into next section, which is about how we plan to structure this in Zeabuz with our system. That means I'll need to give you a short intro to the kind of main structure of our autonomy system, but I'll be brief. Details are not that important here. It's kind of the principles that are important. But what we have, I mean, in any autonomy system, you would have kind of these four main elements. You sense, you comprehend, you plan, and you act. So in our system, the sensing part is perception sensors. So it's radars, LiDARs, infrared cameras, and regular RGB cameras. And they all have their own detection algorithms. So we've chosen here to we've chosen to do detect and fuse, not fuse and detect. So we have kind of separated out the detection algorithms for each individual sensor for some good reasons I'll get back to. Then in the comprehend part, it's what we call situational awareness. Here we have the sensor fusion, so merging these signals from different detectors, doing target tracking and projection. So what are the other vehicles around us and where are they going to be in the future, or where do we think they will be in the future? Then based on that, we have the motion planning. So this is where you make your navigational decisions. So based on this understanding of the surroundings and also of your own vessel capabilities, where should you go? What is the path you should plan? And then you also have collision avoidance. So if another vessel comes along, how do you act in order to avoid a collision? And finally, this is then the autonomy system, right? This is what we call autonomy. This is what replaces the human captain or the human on the ship. Then on the act side, once you've kind of chosen what to do, where you want to go, well, you need to actually go there, so implement. So there we have motion control. There we have more regular systems that are available today, like dynamic positioning, thrust allocation, autopilots, auto-docking systems. These are in use today. And then low-level actuator control, so simply controlling your thrusters and electric motors and so on. And this is automation. And there is quite a lot of confusion on this out in media and amongst and industry. And I see a lot of companies talking about autonomy when they really do automation. So in my opinion, it's autonomy once you start replacing the human and the sense, comprehend, plan part. Doing really good automation is still not autonomy. And then, there are traditional sensors and data sources that you need to do all of this. It's not that important for our discussion now. But what we've seen, at least in automotive, is that some companies have an idea that they want to build systems like this, what I call pixel to pedal, black box approach. So you go right from your perception sensors, and then you do your AI magic, and then you control the steering wheel, and you control the accelerator and the brakes. And everything in between is just a big black box. It's of course an interesting approach from a scientific point of view, there's you could talk a lot about this, but my point is that this is extremely challenging when it comes to assurance. How do you build trust in a system that big and complex with no kind of internal structure? And this is why we have opted to go for a much more modular structure, where we use machine learning and other solutions in a more modularized way. So what we will do is that we will first look at the individual modules, right? So we'll focus on how to build trust in that RGB detector, that machine vision algorithm, how to assure and build trust in the sensor fusion and in the target tracking, how to build trust in the motion planning, and similarly with all these different modules one by one, using parts of this toolbox I introduced, not just simulation, but taking them one by one. That's a starting point. That's kind of your unit testing in an autonomy setting. Then going on to module integration. So once you've gotten there, you can start looking at the bigger modules. So looking at situational awareness as kind of one integrated module and testing and verifying that. Same with the whole motion planning, same with the whole kind of automation system and the integrated automation system. So, and once you've done that, well, then it's relevant to talk about, you know, the full scope, this end-to-end test of the whole system, where you deploy it in a full kind of virtual drive. So, and you need that, of course, you need that too, but you need to work, in my opinion, also on a much lower level. So starting, you kind of build a, you know, a house of cards here, and on all these modules. And if you don't do a proper job of building assurance to all these modules, what you build on top will not be stable and trustworthy. One of the additional challenges that I mentioned several times now is that all this needs to be done kind of continuously, right? So because through the life cycle, you'll have updates and improvements to your algorithms, you'll have new training data, you'll have new functionality you want to introduce, there'll be security patches for cybersecurity reasons, you'll add some equipment to your system, maybe there will come new requirements from regulators or others, which meaning that you get this cycle, that you're in operation with your current system, you get data, you get experience that can be used then to retrain your algorithms, to calibrate the digital twin, to improve your test scope because you have new scenarios that you can deploy, and you do new test and verification, and you deploy your system and you go into operation again. So whatever we build here needs to be usable for this kind of continuous assurance process. All right, so 10 minutes left, I see. So I'll give you just a brief introduction now to the simulator setup that we have very quickly before we have some time for questions. But what we have been doing now in Zeabuz, and actually just this week we had it up and running for the first time, so I'm pretty proud of that because it's the first time, I believe, at least in a maritime setting, this has been done. So what we have our autonomy system. This is then for the milliampere 2, the NTNU pilot ferry. But we have the autonomy system with all these functions that I just showed you, the object detection and situation awareness, the motion planning and collision avoidance and so on, all running in ROS for those interested in that. We have a DP system, a commercial off-the-shelf dynamic positioning system from Marine Technologies, which is used for different other commercial applications, which is then being controlled by the autonomy system. We have a complete simulator of the physics of the milliampere 2, simulating the hull and its movement and the thrusters and the batteries and everything. And then we have a virtual operating environment. So we have a kind of a game engine, which is simulating the whole operational area, and then also the synthetic sensors. So we are actually then providing synthetic, camera images, radar sensors, and LiDAR kind of point clouds to the autonomy sensors. So we're closing the loop completely here with a kind of complete virtual test drive. So it's still very early days, but we just got it up and running. So I think that's pretty cool. And of course, we need to be able to simulate traffic in this scenario. And on top of that, we are going to build, we haven't built, but we need to build a test system which orchestrates and schedules all of these tests. Because again, looking at what they do in automotive, they are doing billions of miles, and we probably need to do some billions of nautical miles as well. So but this is what we're up to. So this is, of course, again, this is one part of the trust building, but a pretty important one, since we have limited opportunities to get a field experience. It's simply too time-consuming and cumbersome and expensive. So you need to do things in simulation. So if I'm lucky and I can get this video to work, yes, I can. So what you see now is just an example from this visual simulator. So you see the milliampere 2. Maybe you can see milliampere 2 is, actually, this is the milliampere, the first one here. And we have some traffic, which is being simulated. So this is all in Trondheim. This is Ravnkloa, where it will operate. So and this visualization here is built on the game engine Unity. Here you can just see a different perspective. Here you actually see the LiDAR sensors. So here you can see the contours of these vessels coming on. So this is then what the sensors would see in real life, and also then what we are simulating and feeding to the synthetic sensors. And the final image here will then be from the onboard cameras. So these are then the cameras that will be used in the object detection. But here we are then simulating the images. You can see the vessels coming on. This is the front camera. You can see them coming here. They will pass out to the left, and they will appear in the port side camera. And you can also see here again the LiDAR point clouds from these vessels. It's not that easy to see. But this is shows high level how it's working. All right, so that's pretty much what I wanted to show you today. Still pretty much on time, talking while both breathing in and out. But when just try to sum up a bit, I mean, I've told you a bit about Zeabuz, what we try to achieve. Here we are in Singapore. For those this is the Marinas Bay Sands. Of course, the Seedbus needs to be there as well. We talked a bit about the challenges of building trust and assuring these complex systems. Looked a bit into automotive and maritime, what's going on there. I introduced you to my preliminary assurance toolbox and how we plan to structure and scope this in Zeabuz, and then a little bit on the simulators that we are using. So that's probably a lot of info in short period of time, but I hope you enjoyed it, and happy to take questions.
Thank you so much, Øyvind, for a very interesting talk, and I think very important for Norway. We have a long tradition in the maritime sector, and this should obviously be important for Norway because of all our fjords, and not only fjords. I live in Fredrikstad. We have a big river down here, Glomma, and the town is at both sides. So one ferry is just going back and forth all the time between these two sites in Fredrikstad. So that would also be a possible test place. I don't know. Do you know Bård Eker or Hydrolift? I think they are also into the similar things. Do you have any collaboration there? Or?
Well, we are together promoting the idea of waterborne mobility, right? So or the water bus concept. I think Hydrolift, Smart City Ferries, and Zeabuz are coming at this from two different angles. They are looking into ferry design and on that conceptual side, and they're also looking into bigger ferries for more people transporting longer distances. We come from the autonomy, and really what we want to do is deliver autonomy as a service. So we need to build some ferries in order to have a market, but it's two different approaches to kind of solving some of the same needs. But we might become partners, but we might not. We don't know.
Okay,
we've had some good dialogue.
Exactly, sounds very interesting, and I was also impressed. So you combine actually LiDAR and camera and also radar and IR. I saw all this, so it's a lot of data coming in there, and also a lot of data to simulate. So this is, I guess, very heavy when it comes to both simulation in the digital twin, but also when it comes to kind of practical life and all the data coming in and how to process them and how to kind of do decisions based on them. So can you explain a little bit further on all this type of sensors and how you're actually combining this and using the algorithms to do decisions then?
Yeah, it's as I say, it's a lot of data, and I think it's and again, in order to have robustness, it's good to have sensors that are based on different physical principles, right? Which is why we have this range. Maybe you only need a couple of them. Actually, the test trials with a milliampere were run only using LiDAR and radar, and you can get quite good performance from that. But but basically we have separate pipelines for these. So maybe if I bring back this slide here. Yeah, so what you'll see, we have kind of separate pipelines here. So the radar data is handled in their own kind of data pipeline, and eventually only providing potential tracks, potential targets to this sensor fusion algorithm. And the same thing then with the infrared processing pipeline, and so on. So the good thing is that since this is modular, you can have dedicated hardware or divide your compute capabilities very structured to handle these different pipelines. Then the sensor fusion target tracking, that's really at the core of the IP that Zeabuz is building on. So we have a licensing agreement with NTNU, and a lot of research has been done on this. So it is this is done using a kind of observer setup. So it's not really using, it's not machine learning in this fusion and target tracking projection. It's more it's a more traditional observer setup. To be honest, this is beyond me to try to explain in more detail how that works. We have one of the founders is a postdoc at NTNU starting with us now over summer that are really into all the nitty-gritty details here. So I'll just make a fool of myself if I try to explain in too much detail. But
you don't share the Elon Musk view that camera is the only thing you need. You will be based on different sensors, I understand.
Yeah. That's I think there are also differences here. I mean, cars are manufactured in millions, right? So every cent you can save on sensors and equipment makes a difference for the finances in a car. So, and I think that's the main argument from Tesla, even though they don't say it. That's really where they come from. It's cheap and simple to just do it that way. For these autonomous ferries, although of course we will try to push the price down as much as we can, the sensor package will not be that critical. So we'd rather have some redundancy and better performance.
Absolutely. No, I think actually also Elon Musk and Tesla states that LiDARs are too expensive and unnecessary in addition. So, but I totally agree. It will be nice. Or that's kind of not the most critical thing here. Here is probably real-time data. I mean, as you said, when you produce like millions of cars, you can also collect a lot of data. But that's also kind of the problem here, I guess, that you will have quite little data compared to the automotive industry. So that's also why you need to rely on simulations.
Yeah, so you can say we need to create the bulk of data from simulations, and then we need to do controlled experiments that we can benchmark towards the simulated data. So we actually, we have a PhD going now in one of the projects that we are supporting. And he's working on exactly that. So in his master's degree, he set up controlled experiments where the target vessels, so the other vessels around, also were instrumented so that you could replicate the exact experiment in simulation, and then you can compare, right? So you can use the real experiments to build trust in the simulation, and then you trust the remaining scenarios in the simulation. That's the kind of core idea.
We have some questions here. I will read up one from Alex Malso first. How will you work to address the recent changes in regulation from the EU? I refer to the proposed EU Artificial Intelligence Act. Who are the best communities in Norway that can get such a product as you approve for a European market? As you,
I would just have to wave my hands and say I don't know.
So,
but I think it's something
how to go forth by approving it for the European market. I think that's kind of the question, approving.
Yeah, but I think if you look at it, there's and I don't know the details of this new legislation, but there's not that much AI involved here, and what we have is pretty much contained, right? So for example, machine learning in the detection algorithms. And from a GDPR point of view, we have pretty good plans on how to handle that, to make sure that we don't store any sensitive data that can track people. So we are thinking about this, but I would need to look further into the requirements there to be able to provide a good answer.
I also just realized that the time flies and it's already 3 o'clock. We have several more questions, but I propose that we kind of end the webinar soon and the recording. But if you're able to stay for a little bit longer, Øyvind, we will still go through some of the questions. So by that, I will just say thank you to all of the attendees that has to go on with their life and do other things at 3 o'clock, while we will have a short nachspiel here afterwards and answer some of the questions. And